Welcome to Spring LIB.
Part A of our question says explain why the secondary maxima and the single-slit diffraction pattern do not occur precisely at beta over 2 equals m plus 1/2 pi, where m is equal to 1, 2, 3, and so on with these integer values. So the intensity at an angle theta is given by the following equation. And first, let's indicate this as part A, where the intensity I at the angle, so we'll call this I sub theta. Let's rewrite that so it looks like a theta value. There we go, is equal to the original intensity I naught times the sine of beta over 2 divided by beta over 2. And all of this gets squared. Or I naught is the intensity at theta equals 0. Beta is the phase difference between the waves from the top and the bottom of the edge of the slit. So the value of the sine of beta over 2 is maximum at the following values of beta over 2, where beta over 2 is equal to m plus 1/2. That's m plus 1/2. All multiplied by pi. Again, where m is 1, 2, and 3, giving the order of the diffraction pattern. So the diffraction intensity given by this by the equation of I theta is equal to I naught sine beta over 2 divided by beta over 2 all squared is the ratio of the sine function and beta over 2. But near the maximum of the sine function, the denominator of the intensity equation also increases, which causes the intensity to decrease more rapidly than the sine function causes it to increase. Thus, the intensity reaches a maximum slightly before the sine function reaches its maximum value. Hence, the secondary minimum does not occur precisely at that beta over 2 is equal to m plus 1/2 pi, or beta sine beta over 2 is maximum. So again, we can say that, let's just go ahead and type out this solution. So we can say near maximum of the sine function, the denominator of the intensity equation increases, causing the intensity to decrease, right? If the denominator increases, the total intensity decreases more rapidly than the sine function causes it to increase. And this is our reasoning for part A, and we can box that in. Okay, we'll move on and do part B now. Where in part B it says, by differentiating equation 7 with respect to beta, show that the secondary maximum occurs when beta over 2 satisfies the relationship tangent beta over 2 is equal to beta over 2. Okay, so essentially we're just going to take the derivative with respect to beta of that intensity equation I naught. So we have d of I with respect to theta being differentiated with respect to beta. And so what we have here is this is equal to, we still have the intensity I naught, but now it gets multiplied by 2 because that value is squared. What's in the parentheses is squared. So then it gets multiplied by what's in the parentheses, which was sine beta over 2. Oh, beta over 2 divided by beta over 2. It's not squared anymore because that squared term came down front. Now we have to differentiate what was inside the parentheses. So this ends up being first what was on top. So this is cosine beta over 2 divided by beta minus, yes, you still have the sine of beta over 2 divided by beta squared over 2. So first you have to take the derivative of the derivative of sine beta over 2, which gives you 2 times cosine beta over 2, or excuse me, 1/2 times cosine of beta over 2. So that will cancel with the beta over 2 that was in the denominator, which is why it leaves you with cosine beta over 2 divided by beta. And then minus sine beta over 2, then you have to differentiate the beta over 2 in the denominator, which gives you that beta squared divided by 2, as well as that negative sign. Okay? So we want to set this equal to 0 because that's when minimum or maximum occurs, is when all of this is equal to 0. So we can say all this is equal to 0 is when the minimum or maximum occurs, since that's what happens with the derivative. But in the above equation, when the first term, the sine beta over 2 divided by beta over 2 is 0, the intensity I theta is maximum. Therefore, the first term cannot be 0. Intensity is maximum, or excuse me, that's when intensity is minimum, is when sine beta over 2 divided by beta over 2 is 0, intensity is minimum. So the first term can't be 0. The intensity is maximum only when the second term of the parentheses is equal to 0. And here, let me just underline it in red. So it's only when this term here is equal to 0. So let's set that equal to 0 and solve for beta over 2. So if we set that equal to 0 and solve for beta over 2, what we end up with is the cosine of beta over 2 divided by beta is equal to the sine of beta over 2 divided by beta squared over 2. Okay, so we can solve this for beta over 2, and we find that beta over 2 is equal to the sine of beta over 2 divided by the cosine of beta over 2. But the sine divided by the cosine of an angle is the tangent of that angle. So this ends up being equal to the tangent of beta over 2. But that's what we were asked to show, so we can go ahead and box that in as our solution for part B. All right, and there's one more part, part C, where part C says to carefully and precisely plot the graphs of y equals beta over 2 and y equals tangent beta over 2. From their intersections, determine the value of beta for the first and secondary for the first and second secondary maximum. What is the percent difference from beta over 2 equals n plus 1/2 pi, and the intensity I equals I naught sine beta over 2 divided by beta over 2 squared. Okay, so we're going to plot the curves for y equals beta over 2 and y equals tangent beta over 2. And the following, the plots that we're going to have are going to show these here. But it says to do it precisely. So in order to do it precisely, I used plotting software because I wouldn't be able to draw it precisely. Even with a nice grid, I wouldn't be able to draw it very precisely. So I'm going to put the plot from the plotting program that I used here. So let me go ahead and do that first. Okay, so this is what came out. Let me move this guy just a little bit. Let me move him up. Maybe make it a little bit smaller. Okay, so in this plot, the green line represents the curve for y equals tangent beta over 2, and the red line represents the curve for y equals beta over 2. So the values of beta for the secondary maximum are determined by the intersections of the two curves. So I put the intersection of the two curves here. You have two of them dotted in black, and you have a couple dotted in gray, but we're just going to consider the two that are dotted in black. So from looking at this figure, you can determine that the value of beta for the first and secondary maximum from the intersections of the two curves, which I have shown, I have the actual axes written out here. So we have y and beta. And so you can tell from their intersection exactly what those y and beta values are. So the two curves are intersecting at the following values. You can see from the figure that one of the values, we'll call it beta 1, which is the first value, is equal to 8.987. And the second value happens at 15.451. So if you're wanting to make these plots, you could do them in a graphing calculator. That's how I did it, and I just plugged my calculator into the computer and imported the plot. So that was a simple way. You could also do it with an online package or something like that, whatever your favorite plotting system or plotting software is. But I found the graphing calculator to be the easiest in this case. So again, here, beta 1 is the value for the first secondary maximum, and beta 2 is the value for the second. So now we can go ahead and do the calculations. We're going to substitute m equals 1 into these calculations. So calculating beta, we'll call this beta 1 prime since it's calculated, comes from the equation that says beta divided by 2 is equal to m plus 1/2 times pi. But m here for beta 1 is 1. So this is 1 plus 1/2 times pi. Or in other words, you can solve for beta 1 prime, and we find that beta 1 prime from calculation is equal to 9.425. And we can do something similar for beta 2 prime, because beta 2 prime divided by 2, oh, I put beta 2 squared, this should be beta 2 prime, just to indicate that it's different from the other beta 2 from the graph, is equal to m plus 1/2 times pi, but this time m is equal to 2. So this is 2 plus 1/2 times pi. So we can solve for beta 2 prime, and we find that beta 2 prime is equal to 15.708. So now that we have the actual and the calculated values for beta 1 and beta 2, we can find the percent error of these values. So let's see. For the first one, we'll say this percent difference, we'll call it percent difference, DIF, is equal to the absolute value of beta 1 minus beta 1 prime divided by beta 1 prime. And this all gets multiplied to turn it into a percent. This all gets multiplied by 100%. So carrying out this operation, we find that this percent difference is equal to 4.65%. Which we can go ahead and box in. And for the second one, we have a percent difference. So we'll call it again percent DIF for percent difference equal to the absolute value we have this time beta 2 minus beta 2 prime divided by beta 2 prime. And then this absolute value again is multiplied by 100% to turn the fraction into a percent. So carrying out this operation, we find that this percent difference is equal to 1.64%.